Hey guys, welcome back to a new video. In this session, we'll be solving systems of 2 and 3 equations using the method of Gaussian elimination. I've previously uploaded 2 videos where we solved such exercises using a more intuitive approach. In contrast, Gaussian elimination is a more algorithmic approach where you simply have to follow a number of steps and the result will roll right out. As always, we'll solve these exercises step by step. And the timestamps can be found in the comment section below, where you can also post any questions you may have. And with this short intro out of the way, let's get into the first exercise. The first exercise consists of the following system of 2 equations that we want to solve. We have 2x minus y is equal to 0. And for the second equation, we have x plus y is equal to 3. So our goal now is to find an x and a y such that both of these 2 equations hold true. And in this video, we'll find this specific x and y using the method of Gaussian elimination. So what is the first step of this method? Well, the first step is translating these 2 equations into a specific matrix that we will work with and will eventually give us the result. Now, what exactly is this matrix? Well, the first row of this matrix will correspond to the first equation. And the second row of the matrix will correspond to the second equation in our original exercise. The first column will correspond to all of the terms with an x. In this case, we have 2x in our first equation and 1 times x in our second equation. The second column, as you might have guessed, will correspond to all of the terms with a y, so minus 1 times y and plus 1 times y. And then the third column will correspond to all of the terms without an x or a y. I call this n. In these 2 equations, this would be 0 and 3. And oftentimes, this column is separated from the other 2 columns by this dotted line. What matrix do we now get in this particular exercise? For x in the first equation, we have 2 because we have a 2 times x. For y in this first equation, we have minus 1 because the coefficient of y is minus 1. And for the element without an x or a y, we have 0. So this element becomes a 0. The same can be done for the second equation. For x, we have simply 1 because our coefficient in front of the x is 1. Likewise, for y, this will also be 1 because the coefficient in front of y is equal to 1. And for n, the term without any x or y, we of course have 3. So we fill that in. And we already have the matrix that we will use to find the specific x and y so that these 2 equations hold simultaneously. If this was step A of the algorithm, then we'll now go to step B, which is the second step. The first thing that we want to achieve with this matrix is make this 2 by 2 submatrix an upper triangular matrix. Now, what is an upper triangular matrix? It means that only the numbers on the diagonal and above them are numbers, and all of the rest of the elements of the matrix have to be 0. So that's the form of the matrix that we want to achieve. Now, how will we achieve this? By doing row operations. This means that we will replace the rows of this matrix with new rows that are the result of adding or subtracting the original rows, which might on their own be multiplied with a specific number. And this might sound quite abstract, but let's see how this works into practice and it will be much more clear. Like I said, what we want to achieve is basically that this element in our matrix is 0, because then we have an upper triangular matrix. How can we achieve that this element becomes 0? By subtracting or adding a number times another specific row. Well, we see that in the first row of this matrix, we have a 2. So what if we now subtract 1/2 times the first row from the second row? Then we would get 1 minus 1. So let's write this down. So our new second row, which I always denote as R2 tilde, will be equal to R2, so our second row that we want to alter, minus 1/2 times R1, so minus 1/2 times the first row. Let's see how this goes in practice and what our resulting matrix will become. The first row simply remains the same because we are not altering it. So let's just copy it. And for the second row, we do have some changes because we see here that our altered second row is simply the second row of our original matrix minus 1/2 times the first row of our original matrix. So let's see how this goes. We have the original element on the second row of our matrix, which is R2, and we subtract from this 1/2 times the original element on the first row of our matrix. So that would be 2. And this way we have our element right here, which is R2 minus 1/2 times R1. And the same can be done for the second element. We have R2, which is simply 1, namely this element, and we subtract from this 1/2 times R1. And R1 in this case will be minus 1. So we simply write minus 1 here. And the same is now done for the third element, which is this 3, which becomes 3, which is the original element, minus 1/2 times the original element on the first row, which is simply 0. So now we can simply calculate this, and we see that we get the following matrix. The first row remains unaltered. And for the first element on the second row, we have 1 minus 1/2 times 2, which is simply 0, which is of course exactly what we wanted. And for the second element, we have 1 minus 1/2 times minus 1. So that would be 1 plus 1/2, which is 3/2. And then for the third element, we have 3 minus 0, which remains 3. And we see that we now already have our upper triangular matrix. We see that we only have numbers on the diagonal and above, and that we have a 0 on all of the other places. And this is exactly what we want. And now that we have our triangular matrix, we go to the next step, which is to make from this matrix that we've got the identity matrix, which is basically the matrix with 1s on the diagonal and the other elements are 0. And how do we again achieve this is by again doing the same row operations. So let's see how we can get 1 on these elements and 0 on these places. For the second row, that's quite straightforward. So the new second row will be equal to 2/3 times the old second row. How do I know this? Well, because if I multiply this row with 2/3, then I see that I will get 1 on this place. And this is exactly what I want. This is already the second row of the identity matrix that we want. So the second row we already have covered. Now for the new first row, let's see how we can get what we want. And what we want is have a 0 on this place in this row. So how do we achieve this? Well, so what if we now just add this row, but not simply add this row? No, we have to multiply this row with 2/3 first and then add it to the first row. Because we see again that if we multiply this row by 2/3, this element will become a 1. And if we add this element with this element, we will indeed get 0, which is exactly what we want. So let's write that down right now. So we know that the new first row will be the old first row plus 2/3 times the old second row. And these are our two row operations that we will now cover. How does this look? Well, this will become a new matrix. And let's focus on the new second row first, because that's the simplest one. We simply have to multiply our old second row with 2/3. We know that 0 times 2/3 is simply 0, so that's okay. Then we have to multiply this second element, 3/2, this element, times 2/3. And we see, of course, that this becomes 1, which is exactly what we want. And then we still have to multiply this 3 by 2/3, and we see that this will become 2. And our new second row is already done. Let's now focus on our new first row. For this first element, we have 2, so the element that we already had on the first row, plus 2/3 times the element on the second row, which in this case is simply 0. Then for the second element, we again have the element that we already had, minus 1, which is this part right here, plus 2/3 times the original element on the second row, which is 2/3 times this element. So we add to this 2/3 times 3/2, and we do indeed see that this becomes a 0. The same is done for the element on the third place. So we have 0, the element that we already had, and we add to that 2 over 3 times the element on the second row. So we add to that 2 over 3 times the element on the second row, which is of course 3. So we multiply by 3. Again, we can simply calculate these very easy sums to get the following matrix. On this position, we simply get 2 again. On this position, we see that we get -1 times this multiplication of these two fractions simply becomes 1. So we have -1 plus 1, which is of course 0. Then for the third element, we have 0 plus these 3 cancels out, and we are left with a 2. So this becomes also a 2. For the second row, we have 0 times 2 over 3, which is 0, and 3 over 2 times 2 over 3, which simply becomes 1. And for this element here, we also get a 2. And this is the matrix that we want, and we're almost there, because this is almost the identity matrix. The only thing that we're missing is that this element here has to be a 1. Now, this is very easily achieved by simply multiplying this row by 1/2. So let's do that right now. So we get 1, 0, 1, because this 2 multiplied by 1/2 is also 1. And we get 0, 1, and 2, which we just copy. And this is actually the matrix that we are ending up with. This is our final matrix. And what we need to do now is to translate this matrix back to original equations. So this is the last step. So let's just copy the matrix. So 1, 0, and then this dotted line 1, 0, 1, and 2. And now we want to rewrite this matrix as a set of equations. And let's therefore go back to our original conversion. We saw that the first row corresponded to the first equation. We saw that the second row corresponded to the second equation. We saw that the first column corresponded to x, the second column corresponded to y, and the third column corresponded to the terms without an x or a y. So let's now do this with our final matrix. We know that the first row corresponds to the first equation, and the second row corresponds to the second equation. We know that this one corresponds to x, and this column to y, and this column to the terms without x or y. And we can interpret this dotted line as being the equality sign. So what do we actually get? We have 1 times x. Okay, so let's write that down. That's just x. We have 0 times y, which is simply 0. Then we have the equality sign, and then we have 1. So we see that we have x is equal to 1, which is already a solution. For the second equation, we have 0 for the x component, so that would be 0. We have the coefficient for the y being equal to 1, so we have y. Then we have the equality sign, and then we have 2 for the element without an x or y. So this simply would be 2. And this is our final result. We have x is equal to 1 and y is equal to 2. And we simply got this by going through very systematic steps. And to make sure that we didn't make any mistakes, we can always check our result so that we are certain that we do have the right result. We simply copy the original equation, which was 2x minus y is equal to 0, and x plus y is equal to 3. And what we can do now is simply fill in the values for x and y that we found. So x is equal to 1, so let's replace this x by 1, and let's replace this x also by 1. And then we have that y is equal to 2, so let's replace this y and this y simply with 2 and 2. And let's see if our equations are indeed right. On this side, we have 2 minus 2, which is indeed 0. So that's correct. In this side, we have 1 plus 2, which is indeed equal to 3. So that's also correct. So we didn't make any mistakes. And we know that this solution is indeed the correct solution. This went very well, so let's go to the next exercise, which is an exercise on solving a system of 3 equations. And more notably, it's the same exercise that I solve on my separate video on solving systems of 3 equations, so you can compare the two approaches and see which one you like most. The exercise is 2y is equal to x minus z as the first equation. 3 is equal to z minus y as the second equation. And for the third equation, we have x is equal to y minus z. So again, we have to find the values for x, y, and z such that these three equations are true simultaneously. And we'll be doing this by using the Gaussian elimination method. In this exercise, before we go into the rewriting this set of three equations as a matrix, we first have to rewrite this set of three equations on their own. Namely, we want to have a set of three equations where all of the x, y, and z terms are on the left side of the equality sign, and all of the terms without an x, y, or z are on the right hand side of the equality sign. Because here we see, for example, that we have all of these terms on the right hand side of the equality sign, and we have this tree here which we would rather have on the other side of the equality sign, which makes the process of transforming this set of three equations to a matrix much easier, and it makes it much less likely to make any mistakes. For the first equation, we move this x and minus z to the other side. So we have minus x plus z plus 2y is equal to 0. For the second equation, we move this z minus y to the left-hand side and this 3 to the right-hand side. So we get minus z plus y on the left-hand side and minus 3 on the right-hand side. And again, for the last equation, we move the y minus z to the left-hand side and we get x minus y plus z is equal to 0. And this set of three equations is completely analogous to the initial set of equations, but these three equations are transformed much more easily into our matrix, which we need to start our Gaussian elimination. Again, we get a matrix which will look something like this. And of course, we know that the first equation, the second equation, and the third equation will correspond to the first, second, and third row of this matrix. And equivalently, the first column, the second column, and the third column will correspond to x, y, and z parameters. And the final column will correspond to the coefficients without any x, y, or z, namely the right-hand side of the equality sign. So how does this look? We see that for the first row, we have for the x component minus 1. So we simply write minus 1. For y, we have a 2. So that becomes a 2. And for z, it becomes a 1 because we just have plus z. And for the coefficient without any x, y, or z, we have simply 0. And here it's very important to keep in mind which column corresponds to which variable. Because we see here, you might make the mistake that because this z is on the second place in this equation, that you might write it down here. But that would be a mistake. You really have to be sure that on the second column in the matrix is the coefficient with the y variable, and the same for all of the other variables. For the second equation, we have for x a 0 because we don't have any term with an x. For y, we have plus 1. For z, we have minus 1. And for the constant term, we have minus 3. And for the third equation, for x, we have 1 because we simply have the coefficient 1. For y, we have minus 1 because we have a coefficient minus 1. And for z, you guessed it, we have simply 1. And for the coefficient without any x, y, or z, we simply have 0. And at this point, we have our complete matrix, which we use as a starting point for our Gaussian elimination. And we have R1 here, R2 here, and R3 here. The second step is, of course, to try to make from this matrix a triangular matrix, which means that we have numbers on the diagonal and everything above it, and all of the remaining numbers will have to be 0. And we're lucky already because one of them is already 0. We see that this element can very easily make 0 if we add to it this element. And this corresponds to a new R3 row, which is equal to the old R3 row plus the old first row. So it corresponds to R3 plus R1, because then we simply get 0 on this first position here. Let's see what the resulting matrix is of this row operation. The first row simply remains the same because we do not change it in any way or form. The same goes for the second row. We can simply copy it because we don't do any operations on it. However, the third row will be different because we see that the new third row, which we write right here, is the old third row plus the old first row. So what does this mean? For the first element, we have of course 1 minus 1, which is of course 0, which is why we did this operation in the first place. For the second element, we have minus 1 plus 2, which simply is 1. For the third element, we have 1 plus 1. And for the fourth element, we have 0 plus 0, which is of course any time of the day 0. And at this point, we have this matrix right here. And we see that we're still not entirely at our triangular matrix. What we still need to do is to get from this 1 to a 0, because at that point we do have a nice triangular matrix. But we see that this can be very easily achieved by simply subtracting the second row from this row, because it doesn't change this 0 at all, because we simply subtract 0 from 0. However, here we subtract 1 with 1, which then becomes 0. Translating this to a row operation, we see that our third row, our new third row, becomes simply the old third row minus the old second row. And let's see what matrix this results in. Again, the first and the second row can be simply copied because we don't do any transformations on these two rows. However, the third row will be different. And let's see how different. So we have for this element here that we have the old third row minus the old second row, which is 0 minus 0, which is of course 0. Then for the second element, we have the old third row minus the old second row, which is 1 minus 1, which is also 0. Then for the third element, we have 2 minus negative 1, which is of course 2 plus 1, and this becomes a 3. And for the fourth element, we have 0 minus negative 3, which becomes 0 plus 3, which is of course 3. And we are indeed left with this matrix, which is indeed a upper triangular matrix, which is what we wanted. And at this point, we go to the third step, which is to try and modify this matrix, again with row operations, to get the identity matrix, which in this case simply is all of ones on the diagonal, and the rest will all be 0. So this is the matrix that we're aiming at. And let's take this row by row. We see already that the third row can be very easily obtained to be a 1 here by simply dividing this row by 3. So we already have our first row transformation, which is that the new third row is simply 1 over 3 times the old third row. Let's now see how we can modify the second row, namely this element should be a 0. So how can we get this element to be 0 without messing up these two elements, because these are already right? Well, we simply see that if we add to this minus 1, 1/3 times 3, then we get minus 1 plus 1, which indeed simply becomes 0. So translating this to a row operation, we get that the new second row is simply the old second row plus 1 over 3 times the old third row. And then we already have this row covered as well. And for the first row, we see that we have to modify two numbers because these two numbers have to become a 0 in order to get the unity matrix. However, let's first focus simply on one of them, namely this number, and then the other number, this 2, we will take care in a next step. So how do we get this one to be 0? Well, quite easy. We can simply add this one and we're already done because it doesn't mess up this number right here because the second row has a 0. So how does this translate into row operations? So the new first row is equal to the old first row plus the old second row. As simple as that. And let's see what matrix we are ending up with if we do all of these row operations. Let's start with the third row. So the third row operation. We simply divide the third row by 3. So this becomes simply this. And here is this dotted line. So this is very straightforward. And we see that this third row here is already the third row that we need. Then let's focus on the second row, the new second row. This is simply this old second row plus 1/3 times the old third row. For the first element, this simply becomes 0 plus 1/3 times 0, which is of course 0. For the second element, we have 1 plus 1/3 times 0, which is still 1. And for the third element, we have -1 plus 1/3 times 3, which becomes -1 plus 1, which is of course 0, which is what we based this row operation on. And then for the fourth element, we have -3 plus 1/3 times 3, which becomes 1. So we get -3 plus 1, which becomes -2. So let's now focus on the new first row, which is simply adding the old first and second row. So we get -1 plus 0, which remains -1. We have 2 plus 1, which becomes 3. And we have 1 minus 1, which becomes a 0. And 0 minus 3, which is of course -3. And this is now the matrix that we will continue with. This is our new most recent matrix. And we see that this matrix only differs from the identity matrix by this number not being a 0 and this one being a -1. It should be a 1. So how can we get this 3 to be 0? Well, we simply subtract 3 times the second row, because then we have 3 minus 3 times 1 is 0. So our row operation becomes the new first row is equal to the old first row minus 3 times the old second row. And this simply becomes the following matrix. So the third row we can simply copy because we don't do any operations on them. Same with the second row, which we also copy. And then for the first row, we subtract 3 times the old second row. So we get -1 minus 3 times 0 still remains -1. We have 3 minus 3 times 1, which is 3 minus 3, which is 0. And then we have 0 minus 3 times 0, which is of course 0. And for the fourth element, we have -3 minus 3 times -2. So we have -3 minus -6, which becomes -3 plus 6, which simply becomes 3. And now we have, again, a matrix that is even more closely looking like the identity matrix. Only this -1 has to become a +1. But this can simply be done by multiplying this row with -1. So this becomes a +1 and this becomes a -3. And we have our final matrix. We have 1, 0, 0, 0, 1, 0, 0, 0, 1, which was what we were set out to do. And here we have -3, -2, and 1. And we can now translate this again to our 3 equations. Remembering that this corresponds to the x, this to the y, and this to the z. And this column corresponds to the terms without an x, y, or z. This dotted line can be seen as an equality sign, and each of these rows correspond to an equation. So we get x is equal to -3, y is equal to -2, and z is equal to 1. And I've written it in this rather funny way because it resembles the way these ones on the diagonal are structured inside this matrix. And this is actually the final result that we have. X is -3, y is -2, and z is equal to 1. And of course, we can and we should always check our result so that we can sleep well because we know that we didn't make any mistakes. So we write our original equation, which was 2y is equal to x minus z. We had that 3 is equal to z minus y. And we had that x is equal to y minus z. So let's see if we didn't make any mistakes. Let's replace the x with -3. So this x becomes -3. Let's see, and this x also becomes a -3. Let's replace y with -2. So this y becomes -2. this y, and this y also becomes a -2 and -2. And to end off, let's replace z with 1. This z becomes a 1. This z becomes a 1, and also this z becomes a 1. And let's see if we made any mistakes. So we have -4 is -3 minus 1. That's correct. We have 3 is equal to 1 minus -2, so +2, which is indeed true. And we have -3 is equal to -2 minus 1. So this is indeed true. And again, we didn't make any mistakes. So we did very well. And this brings us to the end of this video. And I hope that you're now more familiar with how to use Gaussian elimination. And by comparing this video with the other two videos I have, you can choose your favorite method of solving sets of 2 and 3 equations. If you liked the video, give it a thumbs up. If you want to get notified by future releases, consider subscribing. And with that, I thank you guys for watching, and I will see you in the next one. Bye.